last time, if you remember, we have seen in my last video, we have seen meta-analysis of binary outcomes. So specifically, we have actually seen meta-analysis of odds ratios, and specifically we did that from scratch without using any other package. So if you remember, we calculated the weight, we calculated with our hand, we calculated the weight, the variance, and then we calculated the Mantel Henzel odds ratios, and then at the end we calculated the pooled odds ratio and also the confidence intervals by calculating the standard error and the confidence interval calculation, like effect size plus or minus 1.96 times the standard error. That's how we calculated the pooled odds ratio. As I said, the Mantel Henzel method of pooling odds ratio is more popular, but the Peto method is also again very popular in meta-analysis of odds ratios. So today we will pool meta-analysis of odds ratios, but by using the Peto method. The Peto method has its own formulas. We will implement those formulas and we will calculate them by hand without using any other package. This is just to help you understand the theoretical foundation behind pooling the studies. So if you understand how to pool, how to implement those formulas, maybe you can also write your own other package and those kind of things. But it's good to understand what is happening behind the package. So we will do the fixed effect meta-analysis and we will calculate the Peto's method. The Peto's odds ratio, as I said in my previous video, has its own limitations. Just be aware of the limitations. Even though the Mantel Henzel method is more popularly used, the Peto method is also used besides its limitations. So here are the formulas that we need to calculate the Peto method's odds ratio. So here, this is the log odds ratio using the Peto method, and that's calculated by observed value minus the expected value divided by the variance. That's the variance. And then the variance is actually calculated by using this formula. So A plus B, C plus D, A plus C, B plus D. I mean, if you know the this 2x2 table, this A, B, C, D, so that means you have here A, B, C, D. You can take this as A, you can take this as B, and this is C, and this is G, and this is total. That means if you take this is the case, that means the disease, and here are the exposure. So that means this one will be the number of events among the exposed group. This one is the total number of events, non-events actually, the total number of non-cases, or no events or no disease among the exposed group. So if you calculate the odds ratio is calculated by this value times this. I mean, that means the odds of a disease among the exposed, so that means this over this, divided by the odds of disease among the non-exposed group. So that means EC over this value here. So, but in our data set looks like this. And this is actually the data set that I already showed you in my previous video. And here we have the structure of our data looks like this. So here we have the number of events among the exposed group, and here we have the total number of people assigned to the exposed group. And here we have the total number of people in the control group, but within the control group, here we have the number of diseased individuals among the the control group. So here is the structure of our data, but we want it in a way, this A, B, C, D kind of structure. So to do that, we need to do a little bit of calculations. So here we have A and B because it gives us the total number of events, because this is actually designed for risk ratio calculation. So for risk ratio, because the risk ratio is actually probability of events in exposed and divided by the probability of events among non-exposed. For the probability calculation, you usually use the total number of people, but for odds ratio, you simply calculate the ratio of these the cases and non-cases among the exposed and non-exposed. So that's why we need to do a little bit of calculation. So that's so if you know this, if you don't know this value, so you can, if you know these two, The other ones you can calculate them by hand. So that means NE minus EE. Here we have the total number of people, and here we have the number of events. So that means the number of people who are in the exposed group and they don't have a disease, and that's calculated by the total number of people. The total number of people in the exposed group divided by the total number of people with disease. That means the number of event. Total number of people in the exposed group minus the total number of cases among the exposed group. So you get the negative, but exposed. So that's how we get the structure of the data. This is how our data looks like, and here we have some values here. So this is how the odds ratio is calculated. So here the observed minus expected and divided by the variance. If you have already learned a little bit about the chi-square, so this is about how to calculate the expected value. The odds, actually we calculated the expected value for this part, because we are interested in the number of events in exposed in the exposed group. That's what we are interested in. So we need to calculate the expected value for this observed value. Here we have the expected with the observed value, but we need to calculate the expected value for this particular group. So to calculate the expected value, the way we do it is like if you know the traditional chi-square formula, expected value. So that means row total, column total times row total. Row total for this row, this is where this value is located. So that means the row total is this guy, NE, and the column total, where this event is actually here, is this one. So the expected value for this EE is calculated by multiplying NE times EE plus EC divided by the total number of people. That's how you calculate the expected value. Once you have the expected value, calculating the Peto odds ratio is simple. So you subtract the expected value from the observed value, and then you calculate the variance. The variance has also needs the column values. So that means A plus B, C plus D, A plus C, B plus D. So that means row 1 total, this here, row 2, no, this is actually column. So this total times this total times this total here times this total divided by the grand total. That's how you calculate the variance. And you get the row 1 total times row 2 total times column 1 total times column 2 total divided by actually n square. So you add this, you square them, and then you multiply by n minus 1. Again, you subtract 1. That's how you calculate the variance. Once you have these values, once you have the Peto log odds ratio, you have the variance, then calculating pooling is quite straightforward. As we have seen, we do the weighted averaging method. The weighted averaging, so inverse variance, you inverse this variance, and then you take the summation, and then you multiply by that and divide it by the inverse variance, by the variance. So that means you get the weight. That's how you calculate the pooled odds ratio. Once you have the pooled odds ratio, so that means this is the pooled log odds ratio. Once you have the pooled log odds ratio, getting the Peto method is simply exponentiating it. But if you want to get the confidence interval, what you need is, for the confidence interval, is like you need the effect size plus or minus 1.96 times the standard error. And the standard error, you can also get it from here, because this is variance, the standard error. So that means the square root of this variance is you get the standard error. Otherwise, you can also inverse variance. You make a summation of that. So that means you get the total weight, and then you inverse that total weight, and then you put it in a square root, and you get the standard error. Once you have the standard error, it's simple to calculate the confidence interval. So we will implement this, and then we will see it in how it works in the So I created few functions here. I wrote few functions to calculate first the expected frequency. The expected frequency is actually, we need these values. So that means actually as given here. So what we need is, because we need the expected value for this. So that means here, so we need EE plus EC times NE divided by NE over NC. So this function gives you EE plus EC times NE divided by the total. And then, of course, you return the expected frequency, and this function will give you the expected value. The next thing is we need to calculate the variance, and for the variance, what we need the total population, and we need all these values, of course. And then afterwards, it's simply multiplying the row 1 total, column 1 total times column 2 total times row 1 total times column row 2 total divided by that n square. That means this squared times n, n minus 1. So with that, you get the variance. So for the variance, also I have a function here, so you can get, that means the variance of the Peto's log odds ratio, actually. And then you get the n, so that means n is the total population. So we have row 1, row 2, column 1, column 2, and then we simply multiply all of them, and then we square the sample size, and then multiply it by n minus 1. So that will give you the variance. That will give you the variance. The next thing is to calculate the Peto odds ratio. If we want, we can calculate the Peto odds ratio. The way we calculate it is we get the observed value. We need the observed. So here we have this formula, the observed minus expected divided by the variance. It gives us what? The Peto's log odds ratio. If we exponentiate it, of course, we get the Peto odds ratio. So here, this is what we get: observed, expected, variance. So we have the observed minus expected divided by the variance, and then we exponentiate it. So that means we get the Peto's odds ratio. So that's how we calculate the whole thing. So let me rerun. So once you have the expected value, the variance, then pulling is quite straightforward. So let me run this. So the next thing is to calculate the expected frequency, and the expected frequency can be calculated using this the function that we already have. So we have expected frequency, and this function requires these values. Then it will return the expected frequency. So here we have the expected values. So now we create, if we run this, so that means we calculate the expected frequency. The observed frequency would be that value, the one we already have, EE. That's our observed frequency here. So this is observed frequency, but we calculate the expected frequency using the formula that I already mentioned, and that I already and I made a function for it. So the next thing is we need to calculate the Peto variance, because we need this this variance to calculate the weight. So for that we need to call our variance, this one, the Peto odds ratio. So that means here was a formula that we have. I already changed it into a function. So here we call our this EE, and it requires all these values. If we run it, we get the Peto odds ratio. The Peto's variance. Actually, the variance for the Peto's log odds ratio. So here we have, again, if we want to calculate the weight is, the simplest approach will be inverse variance. So that's the inverse variance approach. So that means we simply inverse it. So that means we get the weight. But we want to get the total weight. That's what we need for the pooling. So we calculate the total weight, and the total weight can be calculated using this formula. So that means we get weight for each study, and then we make we sum all the weight, the inverse variances, and we get the total weight. So the total weight, if we actually want standard error for this, the standard error would be square root of that total weight, the total weight. That would be our standard error. And so that means if we use this formula, so that means we can use it for the confidence interval. For our confidence interval, we can use. So let me run this, and then let me check the total weight, how much we have. So if I run this, I should be able to get the weight. So if I run the total weight, that will give me the total weight. But if I square root it, put it in the square root, inverse it, and then that will give me the standard error. So here I have the standard error. So the standard error is this. Now the next thing is we need to calculate the odds ratio and confidence interval and all those things. So to do that, we have to again use this formula. So that means the pooling is calculated by the Peto's odds ratio times by the weight divided by the variance. That's how you calculate the Peto, how you pool the Peto's odds ratio. So to get the Peto's odds ratio, what we need is, let me put it this way, Peto's pooled odds ratio. This is actually pooled odds ratio. So that means what we need is we need to calculate the expected. So that means the observed frequency minus the expected frequency. Actually, this is XP that we already calculated. So the observed frequency minus the expected frequency divided by the variance. That's what you get. So here I have the observed minus expected divided by the variance. This is the Peto odds ratio. So that will give me Peto odds ratio for each studies. But if I sum all of them, so that means I'm doing the weighted averaging. So I'm weighting them. So that will give me the sum total of the Peto's odds ratio. So let me, mind you, here, so this is the formula that we have is this one here. So for the pooled is we take the sum, we take the sum of the observed minus expected divided by the variance, and then we exponentiate. This is actually what we just did now. So what we did is we take the sum, the observed value minus the expected, and then we divide it by the variance, by the variance, the total weight. So if we do that, we get the Peto's pooled odds ratio. Now the next thing is to, let me save this as actually pooled odds ratio. Let me save it this way. And then the next thing is to calculate the standard error. I mean the confidence interval, the lower and the upper ones. Actually, for the lower and the upper one, because after we calculate the log odds ratio, the lower and the upper log odds ratio, we exponentiate. So let me take this actually and not exponentiate this. Instead, I take the pooled log odds ratio. So let me just put it this way. Remove the exponentiation here. So I will remove this. Then so here I'm getting the pooled log odds ratio actually. So that will be the pooled log odds ratio. And here I am calculating because I am not exponentiating it. So that means I'm getting the pooled log odds ratio. The pooled log odds ratio, and then I'm rounding it by 2 significant digits, and then I get the pooled log odds ratio. So if I print that one, I should get the log yeah. So here I have the the pooled log odds ratio. The next thing is what I need is to get the lower and the upper values. The lower would be, so that means, confidence interval. The 95% confidence interval is like you calculate it this way. So that means effect size plus or minus times plus or minus 1.96 times the standard error. That's how we calculate. So now for the lower, what we need is the pooled log odds ratio. That means for the lower we take the actually this would be the lower log odds ratio. The lower log odds ratio. Let me take that out, and then I simply exponentiate, so I get the lower confidence interval for the so that means I have the lower. So for that I need pooled log odds ratio minus 1.96 times the standard error. The standard error, I already said, the standard error is calculated by this. This is the standard error. So that means 1 over the total weight. So if you take that, you get the standard error, and then I simply take it in brackets so it doesn't get confusing. Now the next thing is I take this exponentiated form. So I close the bracket. Maybe to get it better, I put it down here. Then once I have that, it's usually recommended to report in 2 significant digits. Then I will round it into 2 significant digits. The next thing is the upper confidence interval. So the upper would be simple. I will just copy this and then replace few things. So that would be the upper, and then I will replace this minus into plus. So now I have the upper, the lower, and the pooled odds ratio. So for that, if I run these things, I will get everything. So the next thing would be simply to put them in kind of readable format. So let me just get the pooled odds ratio. I will just paste the pooled odds ratio, and then let me just get that this square bracket. I don't need the other one actually. The next thing is, let me take the lower, and then the upper. Then the next thing is to get that. Let me close the square bracket, and then let me add a separator. So the separator would be simply a space. Now I should be able to get the pooled odds ratio, the lower and the upper confidence interval for the pooled. No, this doesn't sound to be correct. So it seems it's getting confused. So instead of saving it, maybe I can simply take this actually, and then replace it with this one, pooled log odds ratio formula. So maybe when I am assigning it, it's getting confused. Anyway, this here we have, that means the pooled log odds ratio, and here I have the pooled log odds ratio. Then that means the confidence interval plus or minus 1.96 times the standard error. As the standard error, as I said, is calculated by the square root of 1 over the total weight. So let me run and let's see. Yeah, still some error. Let me check. Yeah, okay, I saw there was some bracket issue, so that's why it didn't run properly. So anyway, now we have corrected the value. So here I have the pooled log odds ratio, how I calculated that, and then plus or minus. So I take this minus 1.96, then I have the total square weight, the standard error. So that means, and then I round it. Now if I put all of this in one line, so I should be able to get the values. So here I have the Peto's pooled Peto's odds ratio would be 1.35, 1.12, and then the upper confidence interval would be 1.62. So let me add actually one value. Let me add this comma. then we get everything. So here I have maybe I can also add something like this, 95% confidence interval. So maybe I add 95% confidence interval, comma, would be like this. So I have the odds ratio. Maybe I add a little bit of space or comma, so it gets nicer. So here I have the adjusted, the pooled odds ratio. That means 1.35, and its 95% confidence interval ranges between 1.12 and 1.62. So it's overestimating it. Remember last time they're using the pooled Mantel Henzel ratio, we were getting 1.33, except that the confidence interval seems to be a little bit close to each other. Mind this value. Let me just copy it, then bring what we have seen last time and show you. So last time the pooled odds ratio using the Mantel Henzel method was this. See? So let me bring it here, or maybe I can actually copy that one using, so here already have that. Okay, maybe I already have lower and upper, so it will get confusing. So let me just copy this and then show you what we have. So here this is the value we have. No, this one here. So if we get this value, so 1.32, so that means this is using the Mantel Henzel method. So using the Mantel Henzel method, we get a pooled odds ratio of 1.32, but using the Peto method, it's 1.35. So it's a little bit overestimating it. And then 95% confidence interval was 1.1 and then 1.59. Here the intervals are also a little bit bigger. But if we use metagen function, using the metagen, and then if we just use the package, of course using the rounding error, using the rounding, we get a little bit different results. So here we have 1.33, 1.11, and 1.59. So it's basically, if we calculate it manually, so that means you get almost the same result if you use a package. Anyway, that's how you calculate, how you pull odds ratio using the Peto method. As I said, Peto method has its own limitations, and use it according to your data set and your based on your data set and your preferences. Yeah, that's all for today, and I hope we will see each other again in another session. Until then, thank you very much. Enjoy meta-analysis wherever you are. Bye.